Good morning, guys. 23rd day of streaming. Time to get some more good work done. Today, language identification systems. Optimizing what we've got already just to squeeze out that additional performance. And tokenizer. Let's see where we get today. Let me just paste the link. FYI, I'll be going to China tomorrow, so that means over the next 7 to 9 days, I unfortunately won't be able to do daily streams, but after that, I'm gonna keep on doing this again for over the next months, until we wrap this up, until we have something. So, streaming right now, going through various LID systems, optimizing their execution. My rig, HBS tokenizer, etc. Maybe paper reading. Open LID system. Let's go. Share the link. Let me turn on the live chat. And let's go. So, unfortunately, I turned off my computer before I managed to save the LID execution using the NLLB LID model. So I'll have to fix that. Plus, I'm trying to take this default dict and dump it as a JSON, which did not work. Probably makes sense in retrospect. But let's see what we can do there. How can we save? What's the best way to save a default dict? Probably is a pickle. Save a default dict, Python. Okay. Let me see what people say here. Default dictionary in Python. So saving a default dictionary, printing is one thing. Printing is one thing. The best way to save. Okay, we can basically just convert it. Let me see. So we can convert it to a dictionary. And then we can pickle it. Yeah, I don't like this approach. We can dump it as a pickle, sure. And then load it up. Let's see what happens if we just convert it into a dictionary. Let's just come here, run this, and see what we get. I'm gonna try and just convert it into a dictionary and then save it up. Same as here. We'll just be saving, instead of default dict, just a simple dictionary and see whether that will work. It probably won't because I have a NumPy array inside of it. Maybe if we don't save a NumPy, instead we just convert it into a list, and we'll probably have easier time here. Let's see, step by step. Okay, almost done. As you can see, the TQDM progress. And here we are. Okay, now let's grab this and convert it into a dictionary. So what happens if we do something like this and then JSON dump, and instead of this we just wrap it up into a dictionary? This probably also will not work because this is not JSON serializable. So let's go, because of that, let's go up here, I think we just have to modify the logic a bit. Good morning. Well, this is a part of what will eventually I'm planning to build something around these models. So it is a startup in a way, but it's open source. It's going to be open core. We'll always have something that's core open source that people can use as well. That's the idea there. Okay, let me convert. So predictions, extract the predictions, line, label, and the score. How can we convert that? Let me see. Let me kick this off here and stop at the breakpoint. Okay, so let's see what we've got here. So we have this object, and the 0th one is just a tuple, but the first one is a numpy array. So we can convert. What we can do before going here is grab this one and just convert it into a list. Okay, so now that we have a list here, this will still work. Everything will still work, but we'll be able to save this. So let's try that now. Rerun. This failed because tuple object does not support item assignment. Okay, then what about creating a brand new prediction? So prediction is going to be whatever the prediction 0 is, converted into a list. Why deal with tuples? And then this, and again list. So that's a new prediction. Let me stop this one. Okay, I think this is perfect. So now let's wait until we hit here. Yes. And let's now try and save this one. So again, just go back here and convert this into a dictionary and save it up. Okay, unfortunately this path is not saved, so let's just pick something. Let's just do it like this, and let's see whether we manage to save it and what's the final result. So maybe this one. Or this one. Aha. Okay. So this got saved, but because this is German, we basically end up with this being messed up because, let me think. This is a Unicode character. How can we save it? Do we have to specify the UTF-8 in order to render it properly, or what? Let's try again. Let's just try this again. Go back here. And dump, but specify the encoding as UTF-8. Will that work? This does not have. Okay. Dump QJSON with UTF-8 encoding, Python. Okay, so first dump, ensure ASCII false, and then encode. Dump this to a file and just make sure this is okay. Let's try this. Okay, right, and then encoding should be UTF-8, and then if we just dump this, remove this, let's see what we get now. Will this work? Apparently it still did not work, so we have to probably specify this last argument. Ensure ASCII false. So dump the value to the file and make it like this. Will this work? Finally it worked. So that's the final solution. So we have to add the encoding up there and ensure ASCII down there. Okay, let's go back to the code. So we now have this, and what we need to do is, before dumping the data, we have to convert this into a dictionary. Convert it into dictionary and add ensure ASCII false, and also add, although I think this is default, encoding UTF-8, probably redundant for this one, but okay. So to that path in a write mode with UTF-8 encoding, dump this. This should now work. Let's test it. Let me see whether I messed up anything here. I don't think I have. Just convert. We can save it later on without pickle. Okay. And this is it. Kick it off again. This is going to be the first step. In the next one, I'm going to try and parallelize all of this, make it much faster. There is a ton of compute I'm wasting by not running this in parallel. That's the next thing I'm going to do. I'm going to spawn like 32 of these LID processes, and I'm just going to start running them in parallel. We might hit some other bottleneck. We'll see what. Maybe, I'm not sure how memory intensive these are, but we'll see. We can tune the number of processes. That's one thing I want to do, parallelize, and I also want to test out the open LID system. So again, I want to try, and then we can, before going further, then we can just submit the latest code. If that makes sense. Parallelize the computation, contrast the three systems, parallelize the computation, and submit the code before progressing further. Okay. Let's go. Waiting for the breakpoint here. And then let's hope everything works as expected. Until then, we just delete all of this. I don't want to keep spreading the garbage around. I think we can delete this as well. Let's go. This should work. And it did work. Let's just see how big of a file this is. And will this scale once this result becomes very big? Probably will not. Yeah, this will definitely not scale. It's gonna be a huge file if we continue doing it like this. So the reason, let me see, this is the English Serbian Cyrillic. They say Macedonian Cyrillic. This is actually Serbian Cyrillic. Okay, this is just messed up Serbian Cyrillic. Okay, this is somebody using some sort of conversion into Cyrillic without taking care of the semantic of stuff that should not be translated. Let's maybe let me see what else we've got here. Definitely worth digging through this and understanding what was reported. Bila koncentracija na Schillingerov system tag, that's actually Cyrillic. This is not. This is Macedonian. Oftentimes confused with Macedonian. Russian. Whenever it's weird, it's Russian. Okay, at least it's certainly Cyrillic. Okay, let's close that up and see what we got here. Okay, German. A lot of German. For some reason, they thought this is Korean. Definitely not super confident. Wow, super confident that this is KOR. What is KOR? KOR should be Korean, right? KOR? Korean. Okay, this is correct. German is fairly robustly predicted. If it's Korean, we can ignore it. There is no Korean. We can create some heuristics. There is definitely no Chinese or anything, any Eastern language. Let's try Turkish. Is there any Turkish? There is some. This is Turkish. This was also Turkish, I think. This looks like Turkish as well as this one. Or Romanian. Erdogan. R-O-N. Romanian Moldavian. R-O-N. Romanian. Okay, let's go. This looks like Turkish. German seems to be very confident. Deutsch, Latin. If it's first, if the German is the first one, it's fairly confident. If the German is the first one, it's very good. If German, yeah, German seems very confident. Every time German is the first one, it is indeed German. Führer und Reichskanzler. Reichskanzler. Die Geschichtsphilosophie Hegel. Orthodoxe Bischofskonferenz. Reise durch verschiedene Provinzen des Russischen Reiches. Definitely German. Universität Hamburg. This is kind of semi-German and English. Universität Freiburg. Again, this is in German, at least the name. Maybe they didn't translate. Okay, we definitely have the need for a system like this. This is not the best way to go. I'll have to filter this out even further. Let's, before we continue, I need to increase the confidence. Let's increase the confidence until it's like, it needs to be over 95. It needs to be over 95. Let's see then what we dump. And if it's not too much, then, and if it's much more confident, much more precise, in that case, we can kick it off. But I also need to add some parallelization to this code, otherwise it's super slow. I need to have something that I can just copy paste around and plug in new values and have it run parallel. Luckily, we already have that code inside of Stops for processing our data, so I can just reuse some of that. Let's see. Waiting a bit. One more, and then we can see how many we picked up this time. Romanian, R-O-N. So let's save this. Let's see what we got. Okay, definitely much smaller. That's good. Let's go all the way up. Collapse this one. Let's see how much we have here. Okay, it's mostly here, and then okay, we have here German. As long as if it's Korean, we can ignore it. It's literally as simple as that. What's ZSM? ZSM is Standard Malay is ZSM. Let's open up this one. ZSM, Standard Malay. Very poor performance on all of the Eastern languages. YUE is, I think, some Chinese version. YUE, probably just Chinese. So if we open up this, YUE is Yue Chinese. YUE. So as long as we see Eastern, we can ignore. Spanish, Oficina de Extranjeros. This is actually correct, other than the D part. The office for the strangers, like foreign office probably. Pavel Josef Shaparik University. This is actually English, but with a weird name. SLK. What's SLK? SLK. Slovak. That's definitely not Slovak. Well, kind of. The name might be messed with Slovak. German, definitely. Cambridge, the Cambridge Dictionary of Philosophy, Korean. What? Definitely Korean. Never trust these outputs. ZSM, we said that's standard Malay. This, I don't know what this is, but definitely not English. Korean always messes up. German always precise. Korean always messes up, as I said. Italian, Università di Commerciale Luigi Bacon. This is Italian. German always correct. Berlin Hauptstadt der DDR. Again, always correct. Technische Universität München, always correct. French, correct. Incorrect, always when Asian language we can ignore. Always. German, always correct. Italian, always correct so far. French. This is actually seems to be good. The ZSM is standard Malay, and here Malaysia is mentioned as well. So I think it's also correct. Yeah, Chinese, Yue, never correct. French, always correct. NLD, probably Dutch, like Nederlanden. NLD sounds like, yeah, Dutch. NLD from, I guess in German you say Niederlanden. I think that's the name, and so NLD makes sense. I think they also have a similar name in Dutch for Holland, for Netherlands. Or Netherlands, yeah. You also say Netherlands in English. Yeah, we can always ignore this. German should never be ignored, definitely. So if we see big confidence for German, the Beijing star, and what I expect to see the most is German, because we're very connected with them in a way, historically, in tragic ways. Yeah, German always correct. Chinese always incorrect. Candidatura de Unitat Popular. Cat. Is Catalan a language? It is Catalan. Spoken, I guess Barcelona being the quote-unquote capital, if I'm not incorrect. EUS. What's EUS? I'm just gonna put this table on the side so I don't have to switch back and forth. Okay, so EUS is Basque. Basque is also like spoken in, I think, northern Spain or something like that. Yes, just between the border with French. Basque. Italian. Pericoloso delle cose. Il filo, dangerous son or something. Okay, interesting. Okay, guys, with that, I want to now either run the OpenLID system, that's one option, just to compare them, and then we can parallelize them. I think that's the best way, that's the natural way. Let's go and try and run the OpenLID system. So OpenLID. How can we find that one? So there's this fast text library, and I was trying to load the model LID 201, which I downloaded from. Let me just close up all of this. So let's see how to run fast text there. So close all of this. That's the OpenLID system and the paper, which we might read over the next hour or so. Not that many pages, only like 5-6 pages, so we can definitely skim that immediately to get a better understanding of the system. Let's see. So again, this is how to run it. We've done this, and then they say fast text predict. This did not work. I'm not sure how to get this to work on the command line. So they point us here. Requirements. Building fast text is a command line tool. And Python module. So we should surely be able to run in both ways. So let's see. Do they have any running instructions here? Let's see. So building. We're looking for language identification. Okay. Why are they complaining? I think I know. I have to pass in the full path here. That's, I think, everything that we've made a mistake. So we just have to copy the path to this file, and then LID model path. I'm a bit struggling with my shoulder pain, so if you see me kind of making weird faces, that's the reason. Managed to mess it up during the workout yesterday. Actually, before the workout. It was probably a consequence of yesterday's workout. Either way. Okay, so let's stop this and let's just kick off this with no arguments and see whether the loading works now. And okay, it does work. Nice. That's it. That's all we needed. And with that, we can now actually plug this into. We can actually plug this now into our analyze data script already. Let's maybe try a couple of sentences we had here. So I'm gonna grab maybe a couple of these and see how they differ in predictions. This is an easy one, 100% an easy one. But let's test it. Test sentences, something like this. And then let me open up this on the side, split right, and then open up the temporary file we were playing with and find a couple more sentences where I'm curious what this model will say. So according to this model, ZSM is the, as we saw, standard Malay language. Let's see something else that might confuse the model. Let's see what the model says here. This should be easy. Italian. I don't want to try German anymore. I think it's very easy. I mean, if I can do it. Let's see. Alvaro de Madanha de Neira. This should be either Portuguese or something along those lines. GLG. What's GLG? I'm gonna learn a ton of languages through this project, at least to recognize them. I'm gonna become a great system, language identification system. So GLG is Galician. That's like spoken where? Northwestern Portugal, apparently, or no, this is actually Spain. Sorry, Galician. Well, looks more like Spanish to me. Is there anything else that's weird? Italian again. Is there any Cyrillic? Oh, nice. Živo. Okay, let's see this. This is Serbian. Latin script. Okay, having said that, let's quickly test this. Okay, that's it. Let's see what we get as a result. Rerun. German, nice. The second one is Malay, nice. Italian, no. SRD, is that like Sardinian or something? SRD, Sardinian. Wow, I didn't know. My God, they apparently have, it's a macro language. Wait, where is Sardinia? Sardinia is somewhere in the Mediterranean, right? Sardinia. Looks like a nice place. Never been there. In the middle between Africa and Europe. Sardinia. Sardinian language. and then it again says Galician and Croatian. Much better prediction. Much better prediction than this. What's SLV? SLV Slovenian, probably. Slovenian, but that's incorrect. This is either Croatian or Serbian or Bosnian. So it seems already that this model is a bit better, but let's compare them. Let's compare them. So I'm gonna pick this up and just go to the analyze data, go to the LID. We're gonna have two systems. We're gonna load both of them. Model, this is the open model, open LID model, and this is just the LID model. Okay. Looks a bit nicer. Relative path. So we just picked this file's location, grab its directory name, and join that with this name here to get the LID system. And then we build the output directory, and then I'm going to pass models. So instead of a single model, I'm going to pass multiple. And they're run the same way, right? We just run predict. Yes. So in that case, we just pass in LID and we pass in open LID. So again, LID and open LID. Go to LID and change this to models. And now we have to make a for loop. Delete this. There's going to be a ton of refactoring I'll have to do later. Why is this one even used? Okay, this is silly. Okay. So let's iterate over the models. We have a line. Let's do the following. So for model, in models, we need to assert this is a list. Here's instance, models of a list. And then we do the prediction. We map it, and then we save it. Let me see. So corpus language name. Yes, but we want to put side-by-side predictions somehow. Actually, I also want to read the paper later, so let me just put that as a to-do item. Oops. So this whole morning is going to be probably mostly about LIDs. And then I also want to understand a bit better how this fuzzy duplication works. And then we're close to getting the initial set of data for training. How do we want to save this? First of all, this should be model, not models. And next up, we don't want to save this immediately. We want to do what? Line and prediction. For the first system and then for the second one. So we want to append multiple different baselines. Maybe top 2 predictions, just to reduce a bit of the output. And then, because third one is also super unlikely. And then let's see, what's the best format here? We can append a line and prediction as a tuple. We can just extend it to be four tuple within another line, another prediction, or we can make it like a dictionary and then have like LID and open LID as the keys. What makes more sense? I don't know. Let's just try one of those. And these models should be passed in as tuples. This is just the NLLB LID. And this is going to be the open LID. I think that's what it's named. So its name is open LID. Something like that. Go back to the LID function. So this is models. It gives us back the model name and the model. And if this works, if we pass in, we just say, okay, for the model name, add the prediction, and that's it. And then at the end, we just append the actual output here. Should work. It's gonna be slow, but it should work. Let's just test it quickly. Gonna kick it off. Okay, of course I have to pass in the right config. Kick it off again. Okay, line strip. Go. What went wrong now? What? Just a second. What is it complaining about? So LID is a model's list of tuples, and then we go. If we do it like this, will it work? Or we need to pass in a list instead of a tuple? Maybe that's also the case. Let's see. Yes. A list of lists. One of these is gonna work. I don't understand. Why would that fail when we are just loading? Maybe this after all. Kick it off again. Just some trial and error. Okay, nothing works. Why are you complaining? Nah, something's not all right here. Oh. I probably just changed a single one, and that's the ad. Of course. Guess what happens when you duplicate the code? Okay, only if the output is existent. If output exists, in that case, let's see. Yes, that's the solution. Let's go. Run until we hit this line. Okay, output exists. OpenLID had the output. It says this is a German sentence. And it gave us what? What's the actual line? Aha. We can't just put a prediction. We also need to say the line. Previously we were appending. So line and prediction. Get the list. Run again. Nice. Exactly, this is German. Okay, this will work. Now let me just parallelize this a bit. How can we run this in parallel to speed it up? I'm gonna open up the stops repo. And let's see. So we have the filtering stage, we have the data preparation stage. In the filtering stage, are we running? Let me see how we run this. So in the filtering stage, we pass in, we call the filter group on a batch of different data. We have this executor, and then we run with executor batch. I don't think we need to do that. We have this other objects at disposal as well. And then we just submit. Okay, so this is mostly done via the Stopes launcher. We have a better way of doing this. Because for that launcher, well, we might be able to do it like that as well. Not really hard. That's one option. Let's see the other option. The other option is prepare data. In the prepare data, let's see how we do it here in the validation. So we call, again we have launcher. And launcher is what? Self launcher. And self launcher is specified up there somewhere. Let's see, self launcher is again instantiated. We instantiate this. Okay. What if, okay, let's go to, it's going to be the same here. I think the only difference is in binarize. There is this, let me see, module run. So here we have this parallel object. Specify the number of workers. Parallel comes from joblib. Okay. We can also use something like multi-processing pool or whatnot. What's the best option here? There's a ton of way you can do parallelism. There's no standard way of doing it in Python. Async IO as well. I think that's the last thing I used. Let me think for a second. How can we parallelize it? We have a ton of different data sets. We are iterating over them. And then we're passing in those separate files. One way we could optimize it is across the data sets. So each processes a separate file for a separate language. That's one way. Other way would be, but in that case we'll be bottlenecked by the slowest, by the biggest file, and that's going to be a significant difference. We won't be able to save too much. We need to chunk up that file as well. So ideally, we would be processing files in pieces. So we would grab the file and we would chunk that into like 32 pieces, and then we would process it. So that means inside of the LID function itself is where we can build in all of the parallelization. So here's the file. We split it into pieces. We get the length and we chunked it up, and then we call some of these methods. I already have some code for this. I can maybe reuse some of it. Okay, give me just a second, guys. I have to check something on one of my private code bases. Right. Says. Okay, let me see how I do this. You can see this thread pull executor. That should actually work. Okay. Let's try this. Let's see how we can adapt this easily. And will this work? So, we have to import some new packages. Concurrent. And then we need to decide on the number of chunks. You can hard code that here to like 16, for example. Let's start with 8 and see how much we can push it. So it's going to be the number of chunks here. Okay, so now open the file. How can we skip the lines? We'll probably have to do some. Let me see. Submit. We need to have a function that we call. This is going to be the function that we call. After we know, yeah, we can't go like this. So maybe just lead. Okay, we're going to read all of the lines first. Read lines. Where did we call that same code? We did have some of these analyze script functions. Let me just see. language script utils, read lines. Okay, we grab all of the lines. Let's go back to analyze code. So we're going to grab all of the lines. Instead of doing this, instead we're gonna go and grab all of the lines, just read. So now that we have the lines, we're gonna split them up. We can have like, well, they're actually already split. We'll just have to do the stripping. That's fine. And then, wait just a second, I have to go undo a bit. We need the number of lines. We need the number of lines in the file, so we can chunk it up. And so now, and this is going to be the code. This is going to be like the worker, LID worker. It's going to do something like this, given the lines and given the models. And the language code. Corpus name. I'm not sure whether we can pass in a dictionary like this and modified. Probably not. Let me indent this back. Okay. So what do we do now? We spawn that many workers. We call in the LID worker. And then we chunk up the lines into chunk size is going to be, okay, number of lines per chunk is going to be like this. Will this work? Will this work? What's this operator? If we had like 5, I would have to start a debugging session. Whoops. Floor division. We probably need ceiling, not floor. So this would give us 1. In reality, if we have number of chunks, if we have like 3 chunks and we have 5 line, we can do, yeah, we have to do more something like, is ceiling built into Python, or I had to call the math module? I think we have to do ceiling, right? Because if we don't want to miss any of the lines. Okay, and now we just go through the source lines. And we want to go, okay, we can chunk them up immediately. Source line is going to be Yes. Exactly. And then we go to the chunks. We pass in the chunk as the first argument, and then everything else. I'm not sure this will work because of the potential issues, multi-threading issues with the dictionary. But give me a second. What's the result of the... Yeah, we don't need this. What's the result? Can we just modify? One thing is... Okay, this will not work because many of them will be writing to the same corpus name, same line code. Actually, all of them will be writing to the same corpus name and same line code. So we have to think what's the best way to protect this data structure from concurrency issues. How can we do this? I mean, all of them could be doing their own thing, and then at the end we could just merge them. That's one option. Is there something smarter we can do here? Is there something smarter we could do? Not sure. We're all computing a portion. All of them are computing a roughly equal portion of the data, roughly, except maybe for the last worker. So maybe each one of them should just have their own, like a list, data, and then they could just append to the data, and then at the end return back that data, and then here we just grab the data and we append, we extend with the data. I think this might work. This is LID predict parallel. Well, let's try, guys. There is one way to find out. Set the right config, kick it off, enter here. So we count the number of lines. We get the number of pieces. So if I am to multiply this with number of chunks, we get what? This number, whereas the number of lines was this number. Okay, precisely, we need to be a bit bigger. So the last one will handle just a tiny little bit of smaller number of lines. Okay, so here are the lines. And now we keep on submitting. Okay, so this one is going to do what? Did this fail? Too many values to unpack. Why did I have? Because I had a TQDM before. Okay. Let's kick it off again. Run. Let's see what's going on. My memory seems okay. This is just stuck. Wait. Rerun. Oh, we're not even using these. So let's just, for start, oops. Let's just remove this for start. And then try and understand why is this failing. Silently. Number of chunks. Submit the LID worker with the lines, models, and language code for every chunk. Okay, and then here. By the way, can we actually, we'll be able to use the same shared model. This is going to be unique and non-problematic. This is the maybe the problematic part. We're passing in the same set of references to the same underlying models. Are you working on publishing any papers apart from this project? Potentially. We might publish a paper on this project. We'll see. But I'm not in that paper publishing game at all. I'm not playing that game. I'm trying to do different things. Why is this stuck? Why do we only have a single? I can usually debug this. We are doing this. And I know this code works for sure. Already tested it elsewhere. For future, for linking links, we call the submit. And then as completed, for future. Interesting. I've never seen this thread executor getting stuck. Yeah, let's see some of this. Let's just rerun this again. Why is this getting stuck again? Maybe, okay, maybe we need to exit from the, wait, I think this might be the issue as well. Let's just exit from this context of the gzip, collect the chunks, and then we can use them, but we don't need it anymore. Let's maybe run it like this. Maybe there's some weird interaction between the context managers. Yes, apparently that was the issue. Okay, let's go. I do see all 8 executors running. Is it this any faster? It might be like some of the GIL issues might be causing us some problems. Yeah, I think, yeah, this actually will not help at all. I made a mistake. Thread pool executors make sense when you're running something that's IO bound, not something that's compute bound. So this will at best be as fast as what we had before, and it's more likely going to be slower. So we can't actually use thread pool executor for CPU bound tasks. That's the thing. If this runs at all, for some reason I don't see any progress. Is this still running? It is. Yeah, but it's very slow. Okay, let's just get it to work, and then we're gonna modify the logic. We can't use the thread pool. I might have some other ideas. Let me see. Okay, there is some progress, but it's super slow. Let's at least see where it works. But I definitely have better ways to run this. Okay, almost done. Looks like it's speeding up now. Okay. Let's see what the results are. Data. 106, we extend. Okay, let's just exit from this. Get here and see what we get as the output. What's the number of lines we got here? Let's see whether that's consistent with the previous results. We get the keys, index using the XL and English, Latin. See what's the length of this array, of this list. 2535. Okay. And then if we just ran the old way, let me see whether I can backtrack quickly. This was stupid, not checking this in. Quickly rerun this. We should have a deterministic result. And as you can see, this one might be even faster than the quote-unquote parallel version. As I said, we are compute bound, and Python with GIL doesn't really have. It's not parallel doing any parallel execution. It's actually doing it sequentially with some additional overhead. So that's why this was so slow. The last one was even slower than this execution, which is weird. Not something we wanted to do. Let me go grab some water while this is progressing. Coming back in a second. Good morning, SQ. Good morning, David. Yeah. Okay. So our implementation is working, but it's not speeding things up. So there are no concurrency issues or anything of that sort. We don't even need this. I'm not expecting exceptions here. It was just me trying to figure out what was going on. Let me just validate this works quickly. Maybe we do need those exceptions. We don't. Okay. So we can use something like async.io or some something that uses processes. I think this is what we need, probably. Yes, that's pretty much how I understand it. Let's see what people say this versus async IO. Yeah, this is again more for IO bound programs. Yeah, I'm mostly seeing it in the context of working with APIs. Will this have the same interface? I think it will. Let's try this, guys. Let's see how fast or if at all this is. It should be. If it doesn't fail, maybe it has different API. Let's see. Aha. We might need to wait. This might be just retrieving back promises. Yeah, okay. Can't pickle. It's probably struggling as well with the models I've been passing. You probably have to pickle the model. Let me think. What's the best way to handle this? Whoops. Only pickable objects can be executed and returned. Can be executed and returned. So for the return part, we're good. We're returning just a simple dictionary that has list with strings inside of it and in other lists. So this is all fine. This is pickable. The part that's not pickable is models. What happens if we just do this? Terribly inefficient, but let's just see whether it works at all. Will this work theoretically? Seems it's working. Let me see what it's doing to my memory. Okay, nothing serious. We can maybe just kick it off. Wait until we hit one of the breakpoints. Okay, definitely faster. That was faster, right? Let's try more. Let's try like 16 parts. I did hit, my memory was going up, but like we still have much more. Let's see. Let's see how much more we can go. Going up, 30, 33, 34. 60%. Okay, it's done. There seems to be some speed up. It's going to be a function of the number of chunks, number of threads, number of processes. But this is like plain stupid. Every process has to additionally load. Processes are heavyweight in and of themselves. And additionally having to load the fast text model, each of them, that's also slowing us down. Let's see how fast this is, this loading of models. I'm gonna put 2 breakpoints, hit F5, 1, 2. Okay, it was actually fairly fast. So maybe not a problem after all. Okay. Okay, let me see. I should have done some profiling. but I want to see like palpable difference qualitatively. I don't even need to quantitatively see this. Okay. Again, I need to have a serial implementation as well. Let me just, I'm stupid. I'm gonna do this again. Okay, and I'm gonna just go back, and just save this. And now go back. Okay. So we have two implementations. We have the same API, the same signature of the function. We just changed the implementation there. So let's kick this off. Just get some numbers. And then we're gonna try and optimize this a bit more. Put a breakpoint there. Run. This is the parallel one. Maybe we can just put a breakpoint here to see the time before we mess up the log output here. $50. Let's see for this second one. Maybe a bit slower. We can definitely reduce. I think the number 8 was maybe even faster than 16. That's one thing. And then the second thing, we need to remove the load model logic there. Yeah, this is definitely much slower. Like roughly 2x, at least 2x. We are already at 50 seconds here. So for 50 seconds, we got to 48. So roughly twice faster, but we can definitely optimize it even more and quickly. I don't think we need much more time to just optimize this a bit more. Mojo would be amazing here. Okay, so it's roughly going to be 140 which is exactly 2x lower. Okay. A bit over 2x improvement. Okay, let me just quickly now check if we change this to 8. What happens with the speed? So it waits like the first 15 seconds just loading the models, and then it starts running very fast. This is definitely, yeah, this is even faster. Okay, so like 35 seconds. So we are now talking about maybe around 4x improvement even. 36. $150 was 110 seconds. 3x, a bit over 3x improvement. Let me just see what's a good number here as well. What if we do like 7, will that improve the performance or worsen it? After we're done with this, we can just do some preliminary analysis of the two LID systems. Roughly the same speed, 36. Let's try 6. Looking at the other tasks here. I mean, we got 3x improvement. That's not a small thing. And then we'll be able to reuse this code elsewhere as well. So that's cool. The reason I'm analyzing LID is because so far we don't have it in our filtering stage. So I have to include it, and so I'm just analyzing it here, trying different systems and stuff. We also don't have fuzzy dedupe, so we're gonna do that as well. We don't have a specialized tokenizer, which just have the SPM 200, which is, okay, this is a bit slower. Let's now try go above 8 was the baseline, so 8 is the fastest one so far. Let's see what 9 does. I was saying here, tokenizer, we can do this later as well. This is because these first checkpoints will have a smaller scope in number of languages, so we can maybe optimize it a bit, have a smaller tokenizer that's more optimal for the languages we care about, and also a good opportunity for me to learn a bit more about tokenizers, not treat them as black magic. And yeah, then everything else is going to be kicking off the stage. Toxicity filtering is already built in. Okay, roughly the same speeds. So 36 is kind of the peak. Okay, that's what we can pull out with 8 processes. Or maybe we can even put 6, but whatever. 8 is a nice number in the binary world. Okay. Let's see. Process execution, or fast text pickable. Can we make it pickable? Can we pickle fast text models somehow? Okay, Hood, thank you. Thanks a lot. Have a nice day yourself. The completely Python siphon. How does one do this? Not the train. Maybe array might be the answer. Maybe we can use something like array. Let's kind of cope because obviously they had to implement it somehow. We can probably implement it ourselves, but it might be complex. Let me see. Parallelizing the inference. That's what we want to do. Takes. Run pickable objects in parallel in Python. Let's try before I waste any more time on Google. Okay, I think we are kind of hitting the limit here. We probably have to just load the model like this. I think this is good enough implementation for now. I don't want to waste any more time on this. This is something that would need some more work, but we got 3x improvement. That's cool. So let me just remove all of this. Whoops. Remove the time. And you can put the to do here. Fast text models are non-pickable. So this was a suboptimal solution I came up with. Okay. We're left with one more system. I think there's this CLD language detection. Let's just check a couple of these links. I think this latest OpenID paper compared with this one, it was better than, let's just quickly run through some of these articles. Ideally, we would grab and train our own LID system as well. Like that would be the best thing to do. Again, same as with tokenizer, but there is a trade-off. Okay. Okay, this one is actually supported through Opus. When running Opus, you can use lang detect to filter during the download stage of the Opus datasets. We did it before 2010. Croatian is supported, that's cool. But Serbian is not. Interesting. They might have considered Croatian as Serbo-Croatian, who knows. Sentences count. Is this the number of sentences used to train? Yes. So mostly English, and then everything else. Here are some results. Precision goes down here for Croatian, which is similar to Serbian. They get very small number of sentences used, poor precision, recall, F1. Okay. And then there's the lang ID, which is also offered in Opus. Python binding for compact language detect, Google's algorithm originally used in Chrome. Oh, Chrome is notoriously bad with language detection, so I'm not really hyped up about this. Okay. Probabilistically detects over 80 languages in Unicode UTF-8, either plain text or HTML, XML. Which one? The design, all of these are fairly small. The design, I mean, they're called compact language as well, so all of them are fairly small. Even fast text is small. Not designed to do very well on short text. Highly optimized for speed, and that sounds like Google. Python binding to CLD3, evolution and replace the CLD2. Do they have a paper on this one? I think it's literally just mostly very simple logic. Installation. I don't think they ever wrote a paper on this. We can read a bit about it later as well, together with this. What else? Fast text. Okay, they do support the NLLB model, and then there is also the OpenLID, which uses fast text as well. Even the no classifier supports all languages on the first, calculated only on the subset. So these are the results on the biggest dataset containing 300 plus languages. Okay. Let's see this. Okay, it supports some of them, but like terribly. Just nominally supports them. So if you get any, we can create a simple heuristic, like if it's any of these languages below a certain threshold, just ignore the output. But if it's some of the higher confidence ones, like probably German is on top of there somewhere, English, Russian, German, yes. This was the conclusion we had before as well. Let's see, Korean. Korean is super, okay, Korean is actually, oh, good precision. Let me see, Chinese. Do they support, they don't support the, Cantonese they do support. Interesting. For us, it's much more important that we have high quality language identification rather than all of these are optimized for inference speed and stuff. Can we just get something that's super good? So yeah, the best one here is the CLD. Has the lowest footprint, memory footprint, highest throughput. We don't really care about that as much. Fast text seems to be the recommended way. Okay. There might be space for us here to create a better language identification model as well. I'm not sure how these are trained. We can read a bit. This looks like a decent block. Okay, we did read this. Let's see what else here. I think we should enter the paper reading stage a bit. Let me see here. Let's kick off. Let's run and save. Okay, let me let me delete the previous outputs here. We can just delete this one. And let's kick off our run just to see how this new one performs, the OpenLID, just qualitatively, and then we can read a couple of these blogs and papers. Okay, let's see the results first, and then we can read the okay, save this. Let's see what we get. Why am I not seeing the NLLB lead? We have an error here. Something's definitely not all right here. Whoops. Analyze data. If the prediction and store with the model name. We should have NLLB lead. What? Something went wrong here. Just a second. Why would models? We have both the open and the one above. And then we run through it. Model, predict. Oh my God. Let me see, do we want to put it here? So for every line, we do the prediction. Okay, I think this should work. So we messed up a bit. We were overriding the output, so that's why we only kept. Okay, this should be good. Okay. Okay, now we have both. Let's start here. Open lead. Recognize this one as Russian, which is also bad, but and then Macedonian. This is Serbian. This is messed up. This is also Serbian. So it's gonna be mixing up Macedonian and Serbian. Probably it's focusing only on some superficial features like Cyrillic is similar or whatnot, and then it's using more of that than the word understanding. This is Serbian. This is Serbian, but just messed up. Emilia-Romagna, that's like a province in Italy. This is again Serbian. Mostly bad predictions for Serbian. Let's go here for English, German. German. OpenLID messed up here. VEC, is that like Venetian or something? If that's even a language. VEC. Italian. I'm not sure what's VEC. Okay, this is definitely a mess up. Swiss German. Okay, OpenLID is not perfect as well. Okay. Maybe we can use both of them as an assembly. And if both of them disagree with the expected label, then we filter that out. That's an option as well. This is messed up. The mastering architecture is incorrectly. So the problem is most of our sentences are short, and these systems apparently don't really work that well. It thought this is Indonesian with 97% accuracy. It's just confidence. It's just messed up. Okay, this is gonna be fun. Okay. Let's go do some reading, guys. Before that, just a short break. I just need to stretch my legs a bit and my shoulder. So we did run. I don't think we need to run CLD 2 or 3. Those are gonna be even worse. So let's just do some reading and then submit the code, and then we can continue from there. Before that, as I said, just a quick break, 4-minute break, stretching. Be right back. Okay, guys, catch you in a couple of minutes. See you then. Okay, paper reading time. Let's go. These two, let me just extract the paper. Paper is here. Test text. Let's learn a bit about LID systems. Okay. Let's do the reading, guys. An open dataset and model for language identification. Okay, language identification is a fundamental step in many natural language processing pipelines. However, current LID systems are far from perfect, particularly on lower resource languages. Hello, what's up, man? Thank you. We present an LID model which achieves a macro average F1 score of 0.93 and a false positive rate of 0.033% across 201 languages outperforming previous work. We achieve this by training on a curated dataset of monolingual data, the reliability of which we ensure by auditing a sample from each source and each language manually. We make both the model and the dataset available to the research community. Finally, we carry out detailed analysis into our model's performance, both in comparison to existing open models and by language class. Okay. Introduction. Language identification is a foundational step in many NLP tasks, pipelines. It is used not only to select data in the relevant language, but also to exclude noise. For this reason, effective LID systems are key for building useful and representative NLP applications. Despite their importance, recent work has found that existing algorithms perform poorly in practice compared to test performance. The problem is particularly acute for low-resource languages. This work here found a positive Spearman rank coefficient correlation between quality of data and size of language for all of the LID filtered multilingual datasets they studied. Quality of data found a positive correlation between quality of data and size of language for all of the LID filtered they studied. In addition, for a significant fraction of the language corpus they studied, less than half of the sentences were in the correct language. They point out that such low quality data not only leads to poor performance in downstream tasks, but that it also contributes to representation washing, where the community is given a false view of the actual progress of low resource NLP. For applications such as corpus filtering, LID systems need to be fast, reliable, and cover as many languages as possible. There are several open LID models offering quick classification and high language coverage, such as CLD3 or the work of this paper. However, to the best of our knowledge, none of the commonly used scalable LID systems make their training data public. This paper addresses this gap through the following contributions. We provide a curated and open dataset covering 201 languages. We audit a sample from each source and each language making up this dataset manually to ensure quality. We train the LID system on this dataset, which outperforms previous open models. We make this model publicly available, and we analyze the model and the findings to highlight the open problems in LID research. Okay, there is a long history of research into LID using a plethora of methods. For high coverage LID, this work presents a model covering 464 languages, while this work includes as many as 1,300 varieties. Unlike our work, the training data in both cases has not been manually checked for quality. Okay, and varieties where the training data has been curated manually. A ton of African languages. However, as far as we are aware, this data is not easily available. This work released a substantial piece of research aiming to improve machine translation coverage for 200 languages. As part of this, They provided several professionally translated datasets for use as test and development. For this reason, we use their system as our benchmark. I think this is the NLLB paper. Yes, Costa Rusa. Okay. However, whilst they did release scripts to recreate their parallel data, they did not provide or even document the monolingual data used to train their LID system, saying only that they use publicly available datasets supplemented with their own dataset NLLB seed. By providing an open dataset, we aim to facilitate further research. Okay, dataset. The sources. We wanted to be as confident as possible that our dataset had reliable language labels so as to avoid the problems noted in existing corpora. We therefore avoided web crawl datasets and instead chose sources where we felt the collection methodology made it very likely that the language labels were correct. The majority of our source datasets were derived from news sites, Wikipedia, or religious texts, though some come from other domains, for example, transcribed conversations, literature, or social. A drawback of this approach is that most of the text is in formal style. Further work could collect data from a wider range of domains, whilst maintaining trust in the labels. Yeah, well, this is probably something that's gonna immediately dismiss this model for many of our data, because most of our data comes from crawls and mined, like as a mined dataset. We checked that each dataset was under an open license for research purposes or described as free to use. Okay, language selection. Our initial aim was to cover the same languages present in the Flores 200 evaluation benchmark, so we could use this dataset for evaluation and compare our results directly with the NLLB paper. However, during the curation, we decided to exclude 3 languages. First, though Akan and Twi are both included as separate languages, Akan is actually a macro language covering a language continuum which includes Twi. Given the other languages in Flores 200 are individual languages, we decided to exclude Akan. Secondly, Flores 200 includes modern standard Arabic written in Latin script. It is true that Arabic dialects are often written in Latin characters in informal situations. However, MSA is a form of standardized Arabic which is not usually used in informal situations. Since we could not find any naturally occurring training dataset, we excluded MSA from the dataset. Finally, we excluded Minangkabau in Arabic script because it is now rarely written this way, making it difficult to find useful training data. Interesting. Let me read this about Arabic again. Includes MSA. Okay. Manual audit process. The first step in our manual audit was to check and standardize language labels, as these are often inconsistent or idiosyncratic. We didn't still start playing with Arabic data. We'll see later once we wrap up the HBS languages. We chose to copy the language codes in NLLB from NLLB and reassign macro language or ambiguous language codes in the data sources we found to the dominant individual language. Whilst this resulted in more useful data for some languages, for other languages we had to be more conservative. For example, we originally reassigned text labeled as the macro language Malay to standard Malay, but this led to a large drop in performance as the former covers a very diverse set of languages. 2 of the authors then carried out a manual audit of a random sample of all data sources and languages. One, a native Bulgarian speaker, able to read Cyrillic and Latin scripts and Chinese characters, and the other, a native English speaker, able to read Latin, Arabic, and Hebrew scripts. For languages we knew, we checked the language was what we expected. For unfamiliar languages in the script, we could read, we compare the sample to the Universal Declaration of Human Rights. Or failing that, to a sample of text on Wikipedia. We compared features of the text which are common in previous LID algorithms and could be identified easily by humans. Similar diacritics, word lengths, common words, loan words, matching the right cultural background, similar suffixes and prefixes, and vowel consonant patterns. For scripts we could not read, we checked that all lines of the sample matched the script in the Universal Declaration of Human Rights. Okay, so basically 2 of them went and did manual audit. They seem to be polyglots, plus they consulted some of these reference documents like from Wikipedia or the UDHR. Oh, that's awesome. 100%. We're gonna focus on Arabic. We will need people like yourself to help out. Did you check the language champion doc? Do add your name there if you didn't already. It's in the Open NLLB channel among the pinned posts. You'll find it. Okay, so pre-processing. We kept pre-processing minimal so that the process was as language agnostic as possible. We used the scripts provided with Moses to remove non-printing characters and detokenize the data where necessary. We then filter the data so that each line contained at least 1 character in the expected script to allow for borrowings. Finally, we followed these 2 papers and sampled proportionally to this, where this is a fraction of lines in the dataset which are in the language L. This aims to ameliorate class skew issues. We then filter the data so that each line contained at least 1 character in the expected script to allow for borrowings. What do they mean by this? Why would you keep only a single character? Aha. Okay. In the sense, yeah, okay, just a heuristic. Where, if, for example, in Serbian, if you start using too many English words, it can still be a valid sentence, but it's hard to estimate that, as we discussed over the last couple of days. Okay, the final dataset contains 121 million lines of data in 201 language classes. Before sampling, the mean number of lines per language is 602,000. The smallest class contains only 500 lines, and the largest 7.5 million. They trained fast text LID using the command line tool. It embeds character level engrams from the input text and then uses these as input to a multi-class linear classifier. That's how I understood these systems as well. So they basically do, so again, it embeds character level engrams from the input text and then uses these as input to a multi-class linear classifier. Curious to understand a bit better how this exactly works. But basically they find some engrams, I'm not sure what n will be, and then they embed that, so they have to have a huge embedding table, and then they just do some simple MLP on top of that probably. We use the same hyperparameters as the NLLB paper, which we list in Appendix B. We trained our model on one Ice Lake node. Each node has 76 CPUs and 256 gigabytes of RAM. Our model takes roughly 2 hours to train and contains 60.5 million parameters. Inference over the 200,000 lines of the test set takes 22 seconds. That's definitely fine. We'll probably have around, well, after filtering, I think we currently have exact filtering. We have around like 90 million per language. So like even in that worst case, what would be our runtime? Like 270 million. And then I need one more zero. 270 million. And then divided by, divided by 206. And then multiply that with 22.4 seconds. So that's this amount of minutes and this amount of hours. 8 hours. So like we would need roughly 8 hours to do inference. I'm not sure by inference, what's their inference machine? Do they still use, do they parallelize across all 76 CPUs, or is it a single GPU? Or I guess it's not a GPU, it's gonna be, they run all of this on CPUs. Yeah, okay. Just reply to Chris. I see it's 60.5 million params. Also, my usually interest in Southeast Asia. What's CJK? Chinese, Japanese, Korean. Even still, most of the time your best bet would be to use either a fast text-based model or build one with fast text. Okay. Awesome. What's your name again? Okay, let's see the evaluation. We use Flores 200 benchmark provided by NLLB for evaluation. It consists of 842 distinct web articles. For each language, 997 sentences are available for development and 1012 for dev test. Okay. We compare our model's performance to two other open source LID systems, the NLLB 218E and the PyCLD3, which is the Pi binding around the CLD model from Google, Quickly, let me check the name of this model. Fast text language identification model pin. Okay. Majid. Abdul Majid or Majid. Nice. Nice to meet you. We discussed how we ensure a fair comparison below. So NLLB is a fast text model as well. We were surprised to discover that whilst it does cover 218 languages, it only includes 193 of the 201 languages in Flores. Okay. We discussed the reason to merge Akan and Twi in section, but we judge Arabic dialects to be close to but distinct languages. Our model performs poorly on Arabic dialects with the highest F1 score of only 0.4894 Moroccan Arabic. This is likely to the general difficulty of distinguishing close languages combined with particularly sparse training data. We assume these poor results led to Arabic dialects being excluded from the NLLB LAD classifier. We remove 8 Arabic dialects from the test set when comparing our model and NLLB, leaving 193 languages. CLD3 is an Ngram-based neural network model for LAD. It uses different language codes to the other two models. So we normalize all predictions to BCP47 macro language codes to allow fair comparison. We test on the 95 languages that all models have in common after normalization. And then the results. Majid. Nice. Our results are given in table 1. We evaluate all models using F1 score and false positive rate. We report macro averages to avoid down weighting low resource languages. Following this work, we report FFR to give a better indication of real world performance when there is a significant class skew. We achieve an F1 score of 0.927 and FPR of this. We also outperform both NLLB on the mutual subsets of Flores 200 modified. Since NLLB and our model share the same architecture and the same parameters, we attribute our success to our training data selection and manual audit process. Notably, our F1 score jumps to 0.959 and FPR falls to 0.020 when we exclude the 8 Arabic dialects from the test set to compare with NLLB. The 95 languages covered by CLD3 and NLLB in our model are mostly high resource, and so it is unsurprising that we achieve the highest F1 score and lowest on this subset. We notice that the Pearson correlation between the number of lines of training data and F1 score for each language is only 0.0242. This is not unexpected. Some of the least resourced languages achieve perfect scores on the test set due to high domain overlap, whereas the higher resourced languages might get lower scores on the test set but have better robustness across domains. Okay, so you cannot predict based on the resourcefulness of the language, quote-unquote resourcefulness. High availability of data. You cannot predict the score because there is also the domain shift issue. Okay, performance by language category. Using the taxonomy and list of languages from this work, we labeled each of the languages in our dataset according to its level of data availability, 0 through 5. We leave out 5 languages missing from the taxonomy. plus the 8 Arabic dialects not covered by NLLB. Table 2 compares the mean F1 score and FPR for our model and for the NLLB. So they're better across the spectrum, or on pair. We note that class 0, the least resourced languages, show the smallest change in performance. We speculate that this is an artifact of the curation of our trained dataset. For the best resource languages with more sources to choose from, it is likely there is a significant difference between our trained data and that used to train the model in NLLB. However, for the least resourced languages, the sheer lack of resources means that overlap between our data and that used by NLLB is more likely. They suspect that's the reason they see such a small difference in table 2. Okay. Supported languages gives the number of languages the classifier claims to support. Okay. Case study, Chinese languages. Despite our model outperforming NLLB overall, NLLB achieved a noticeable higher F1 score on YUE Chinese, on U Chinese. Figure 1 shows the confusion matrices for our model and NLLB between the 3 Chinese languages. Our model performs well on simplified and traditional, but almost never predicts U Chinese, instead of classifying it as Chinese. The NLLB model is also unable to distinguish between U and traditional, but mixes the two classes instead. We asked 4 native speakers to inspect our training data and the Flores 200 test set. They noted that there was a mismatch in domain for U Chinese, as much of our training data was written colloquial U Chinese, whereas the test set contains a formal writing. Furthermore, they were unable to distinguish with high confidence between U and traditional, as the two languages are very similar when written formally. This is an example of a wider problem with LID. The language covered by a particular label may vary widely, making single label classification difficult. That's fine. For example, for us, what I need currently is just HBS or non-HBS. And there is a very small difference between Montenegrin, Serbian, Croatian, and Bosnian, but between them and other languages, for a human being, it's very easy to guess one or the other. So yeah, shouldn't be too big of a problem for our use case at the moment. But in general, yes, when we're dealing with 200 plus languages, this is going to be a problem. We present an open dataset covering 200 more languages. Okay, cool. Yeah, so this might be misleading how the model performs on the actual out of the distribution data. Okay. Cool. Let's see the confusion matrix. So here's it for NLLB. some mixing up there. But this one is completely terrible with U. Okay. That's it. That's this paper. Again, these results should be taken with a grain of salt, as they are only on a very, very small benchmark. That has a very particular domain from Wikipedia, so very formal in nature. And we have a ton of data that's not of that sort, so we might have issues. Let's see what's up in the appendix section. Data sources. Hyperparameters. Two to 5 for n-gram. For word n-grams, only 1. Okay. Performance by language. So you can see here, only with 6,000 sentences, very high score. That's what I said by there is no correlation between the number of sentences and the score. Okay, let's also read the paper from FastText just to understand how these models work. You will find it in a second. It's a very, very old technique. We can just skim the part that we care about on the language identification. Let me see whether there is any relevant information here. Okay, this is more of a checklist for them. Okay. Cool. So that's that paper. Let's skim through CLD, README. They don't have a paper. So it's a neural network model for language identification. This package contains the inference code and a trained model. The inference code extracts character n-grams from the input text and computes the fraction of times each of them appears. For example, as shown in the figure below, if the input text is banana, then one of the extracted trigrams is Anna, and the corresponding fraction is 2 out of 4. Because what we have N appearing here, and then N appearing here. What do they mean by 2 out of 4? Because there is, okay, yes, because there is 4 possible trigrams. The n-grams are hashed down to an ID within a small range, and each ID is represented by a dense embedding vector estimated during training, hashed down to an ID within a small range. Okay, so that means they map potentially multiple different engrams to the same code or what? Because there's, yeah. And they use that to embed. The model averages the embeddings corresponding to each engram type according to the fractions and the average embeddings are concatenated to produce the embedding layer. The remaining components of the network are a hidden ReLU layer and a softmax layer. To get a language prediction for the input text, we simply perform a forward pass through the network. Greetings from the Montenegrin airport. Greetings. Hello. Safe flight. So what they do, again, they extract all trigrams, all bigrams, all unigrams. They then hash those to get the ID from some table, and then they get the embedding. And then they just average the embeddings for all of these different classes of engrams, and then they concatenate them. Okay, I think it's a very similar logic for the fast text as well. Okay. Here are the languages they support. And credits. Okay, that's it. Let me see whether there are any insights here. Okay, let's go. Let's see fast text. Let's skim fast text, and let's see. Also, this blog looked very high quality. Let's skim through this. A language identification task, also called language detection, consists in determining the natural language that the text is written in. Okay. In politics, language ID is used for marketing purposes. It can be the first step in any project. So for us, it's going to be filtering. Indeed, if you do not know the language of a text, you will not be able to tell which language-specific model should be applied, unless you're using a multilingual model. Today, a significant amount of user-generated text content contains a small number of characters, mostly due to the increasing use of social media. And the limit of characters in a TikTok comment is 150. Even if a given method achieves good results on large text, it does not necessarily generalize to short texts, which are known to be much more challenging for the existing LangID methods. We did notice that immediately. I tried running the NLLB, and immediately, if I didn't include some thresholding, if we were just running it on smaller text, it was completely off all the time. All the time it was thinking that some English words were not English, and then it was messing up the detection. The survey showed a lack of interest in short text, which is recently considered a much more challenging problem for state-of-the-art LangID techniques. So they evaluated for short text language. Both classical ML approaches and state-of-the-art deep networks. Evaluated on different datasets containing short text originating from social or reviews. Okay, background. Text. A text is the original words of something written, printed, or spoken. Short text. Under 100 characters. Label. A tag attributed to a text. Dataset. Text classification. Language. Script. We found 7 datasets. We then considered a dataset for our review. Less than 100 characters. 5 datasets at the end. Okay. Number of texts, number of languages, number of texts per language. Mean number of characters. This is very short. Okay. Tweet LID 14 task. Basque, Catalan, Galician, Spanish, and Portuguese. So this is like, okay, Spanish and Portuguese. Basque is apparently spoken between France and Spain. Catalan is like northeast. Galician is northwest of Spain. We also use open subtitles ourselves. Language detection. Tatuiba. Popluca. Okay. The most recent and newest techniques for LangID. Why didn't I'm not seeing anybody running transformers, I guess just because it's oftentimes used and needs to be lightweight. Originally published in this paper, one of the first approaches, fast response time. The method is based on a strong set of predefined features that are computed using information gain that is applied to a different set of n-grams. The latter features are then fed to an Eve-based classifier for training using a corpus of various texts originating from different microblocks. Results back then were quite impressive given the level of competition in 2012. However, as you will see in the next subsection, the ultimate NLP package was published by Jolene et al. Okay. Bag of tricks for efficient text classification. Test text was originally published by Jolene as a library for general text classification. Later on, published in his blog post, a new open source model for language identification is able to recognize more than 170 languages instantly. We can check out this. The model was trained on 3 main datasets. Apart from using a huge amount of data, this model makes use of subword features to achieve high competitive accuracy. For example, if the given word is skiing, then the corresponding subwords or n-grams are generated and used as input features for the model. Skiing, ski, key, okay. A key advantage of generating subwords is that misspelled words can be corrected somehow, since not all subwords will be misspelled. Weight quantization. Feature selection. Okay, and then there is a CLD v3. Okay, we've seen this in the README. XLM Roberta based language detection. Okay. In 2022, we cannot be talking about NLP tasks without mentioning the famous transformer based. This is why Lucas Papariello took it upon himself to investigate the use of the most recent multilingual transformer based model called XLM Roberta. Published by this work, the model was trained on language identification dataset hosted on Hugging Face. The model supports 20 languages only and is considered to be one of the state-of-the-art approaches for various NLP tasks not limited to text classification, such as question answering and name entity recognition. Okay. Let's see that. I'm curious about this one. Fine-tune on the language identification dataset. Arabic, Bulgarian, German, English, Spanish, French, Hindi, Italian, Japanese, Dutch, Polish, Portuguese, Russian, Swahili, Thai, Turkish, Urdu, Vietnamese, Chinese. The training set contains only 70K samples. Nice. Benchmarks. Not super convinced. Hola is classified as Swahili. Hola. Spanish hola. Swahili. Okay, let's go further. LSTM LID. Apple published recently a blog post describing their internal solution for LangID. By focusing on shorter texts, Apple is pioneering the research for language detection on very short strings with their proposed LSTM LID solution. However, Apple did not publish the corresponding code, thus motivating this work to reproduce the results while open sourcing their code. Okay, the method first applies Unicode-based written script identification. and then forwards the text to the corresponding LSTM-based architecture to classify the language. Okay. Unicode-based written script identification. I'm not sure what they mean by that. And then forward the text to the corresponding LSTM-based architecture to classify the language. For each script, we would have an independently trained network that would predict the language given the input text. Specifically, each character would pass through the LSTM for which we predict a single language. Okay, eval accuracy and inference time. Given that not every model predicted the same languages, we had to come up with a solution to compare them accurately. Since we are interested in benchmarking how LangID models behave on really short, we wanted to calculate the accuracy of the model's prediction for each length of text x-axis. The following graphs depict these results for each dataset. Okay, so only when you go above 100 is when the models start becoming more confident. And as you can see, here we were just playing with 25. So that's why these papers are important. Now we can do something like increase the threshold here. So which is the best one? Interestingly enough, XLM Roberta, given that it's a transformer, is like way below. It seems that this Pareto frontier is mostly LSTM and fast text. So I guess fast text is just the winner. As we can see on the preceding graph, there are three distinct groups of the models. The singleton CLD-V3. It's a super interesting blog. Okay, as we can see in the preceding graph, there are three distinct groups of models. The singleton CLD-V3, the group lang id xlm Roberta base and the group LSTM fasttext, which have similar accuracy. CLD is the worst one without a doubt. Open subtitles. LSTM is the best one here. Fasttext not as good. LSTM works better. Clearly, LSTM works better for this dataset, and the XLM also obtains good results for text under 50 characters and similar results to LSTM when comparing the accuracy of the texts over 50. Okay, and finally, here, for this dataset, the results are harder to compare as it includes only 3.7 thousand texts under 100 characters. Tatuiba, again LSTM and fast text. And then Palpuka. Look at this chart. CLD3 is just a madness, how bad it is. Because the XLM Roberta is trained on this dataset, we only considered the test set for our benchmark to avoid biases. However, one cannot negate the fact that XLM Roberta would still have an advantage when being compared to other models on this dataset. By observing the figures above, we can spot a high accuracy variance between models, especially for extremely short text, thus making it harder to determine the best model in these scenarios. Okay, so fast text and LSTM. We can also see that CLDV3 and LangID don't perform very well on short text. Finally, the inference time of a model is a decisive variable. Yeah, fast text is like 2 orders of magnitude faster than anything else, especially LSTM. This table allows us to observe 3 different groups of models. But did they run transformer on a GPU or what? Like, you can still parallelize this massively if you have GPUs. For me, this would not matter as much. Running fast fast text on CPU or parallelizing across my GPUs. I don't know. LSTM, of course, scales slower and slower with time. Why is the curve so much weight? I mean, transformer is also autoregressive. Why is this so flat compared to LSTM? Aha, because yeah, we're not. Yeah, we're just doing a forward pass. Okay. The inference time for Excel and Roberta does not increase. For LSTM, this augmentation in inference time is obvious. Yeah. Conclusion. Language identification is an abundantly studied problem, specifically in NLP, where it can be the first step in many projects to determine which language-specific models to choose. However, lang ID on short texts is more challenging, and existing surveys on the subject often lack short text example datasets while limiting their comparison to a couple of techniques on 1 or 2 datasets. More challenging, existing surveys on the subject often lack short text example datasets while limiting their comparison to a couple of techniques on 1 or 2. Therefore, in our blog post, we fill this gap by presenting one of the first comprehensive benchmarks of 5 LangID models on 5 different datasets, focusing on short text examples. We observed that CLDV3 do not generalize very well. Transformer performs well for the task at hand on some datasets while having lower accuracy in some others. And LSTM and fast text both achieve the best performances for the overall benchmark. To go deeper into the work we did here, yeah, well, transformers were definitely, somebody took like a dataset and fine-tuned the XLM. That's not really a serious method. Further investigating transformer-based models trained on larger datasets with more languages. Yeah, that's what I thought as well, just doing some model assembly. Cool. So unless somebody trains a serious transformer, I mean, fast text is definitely the only one that scales decently. This is how fast text was announced, and this is the paper behind fast text. Let me see what Chris was writing. You will be surprised what would be possible with proper lang ID, but if it is difficult for native speakers, it might not be possible. Are you open to a two-pass process, or do you want it to be one comprehensive LID? Okay. Let me just skim through this blog, see what's up here. As text, large. Not much better. Training your own language detection. First, we need a dataset to train our model. Let's download the training data. First model. We can now train our first model and test it on the held out data. Using subword features. The first way to improve our baseline model is to use subword features, which enhance the classifier by taking into account the structure of words. It uses a simple and effective way of incorporating such information. Each word is represented by the set of all character engrams of a given length appearing in that word. As an example, when using subwords of length 3, the word skiing is represented by. A key advantage of these features is that out of vocab words such as misspelled words can still be represented at test time by their subwords representations. This makes text classification much more robust, especially for problems with small training sets or for morphologically rich languages. Users can enable these features by simply specifying the value of the minimum and maximum character engram size with the command line options with min n and max n. And finally, we can compress it. How does the Mahler quantization work? It's quite simple and relies on two operations: weight quantization and feature selection. Okay. This is the paper. MIT license, cool. The models were trained on data from Wikipedia, Tatuiba, and South. SE times stands for, I think, Southeast Europe or something. Only runs on CPU. Okay. Let's check out, let's skim this paper quickly, and then we can think of the next steps. Okay. Enriching word vectors with subword information. So that's that whole engram business they are doing. I think it's both of these techniques are super similar, both fast text and CLD3. Let's just skim through this paper quickly. Continuous word representations trained on large unlabeled corpora are useful for many NLP tasks. Popular models that learn such representations ignore the morphology of the words by assigning a distinct vector to each word. This is a limitation, especially for languages with large vocab and many rare words. In this paper, we propose a novel approach based on the skip-gram model, where each word is represented as a bag of character n-grams. A vector representation is associated to each character n-gram, words being represented as the sum of these representations. Our method is fast, allowing to train models on large corpora quickly, and allows us to compute word representations for words that did not appear in the training data. We evaluate our representations on 9 languages, both on word similarity and analogy tasks. By comparing 2 recently proposed morphological word representations, we show that our vectors achieve state-of-the-art. Okay, let's see. First language, identification, is it mentioned? Identification. Okay, definitely not method explicitly. Okay. Training data on performance. We train models on a fraction of the full Wikipedia dump. Language modeling. Okay. There's no need to read it. That's it. We are done with paper reading. Let me maybe move, instead of deleting these, I'm just going to move this to some like literature section or something. LID perf on short text. Google's CLB3. Apparently on a specific Flores 200 domain. Okay, we are back here. So what can we do? What can we do? If we train a system to just distinguish between HBS and non-HBS, that will probably be more powerful than all of these other ones, because we ultimately don't really care about, for our use case, we care about HBS versus non-HBS at the moment. How fast would it be to train such a system? I don't know. Optional. we're just opening a can of worms here. There is always a ton of work one could do. Okay, guys. For now, I'm going to submit the changes I have here, and then we're going to continue. I have to pay the technical debt. So let's go here, copy the path. Let's see what we added. Let's see this temporary file. Let's start from the beginning here. Okay, this one, we can delete it. What next? Large number of sentences, pickle. We can remove a lot of these. Remove language number. Okay, exactly. And then custom config. We have data temporary. What do we have in data temporary? Okay, this was just testing the malloc before we integrated it into analyze data, so we can delete that as well. We can delete this as well. And then parse makoku. We definitely care about that one. Data output text. Can remove that one as well. LID. Download. Chunk. YouTube Croatian. Remove that one as well. Up there, mostly YAML, Py, we can ignore this one. Yeah, there's going to be a ton of stuff here, but I don't think it will take a lot of time. Let's start somewhere. Let me see. What do we want to submit here? It's mostly in the data. Data. All of these other ones we can ignore. And then here as well. Data. And then we can ignore all of the other ones here. It's literally just a data folder. So let's start. Let's go step by step here. Let's see parse makoku. This is how I parsed it. I would have to add some updates to the README. Oh my god, my camera just died, guys. I'll have to restart again.